Everyone. Thanks for joining our High Voltage Cable Symposium. I'm Giacomo Bastinel. I'm the chair of the IEEE Student Branch Leuven PES chapter. Since we are slightly late, I will just cut short on the IEEE Student Branch Leuven. Probably you already saw these slides. It's just, yeah, we are the local branch IEEE. These amazing people are helping us in organizing the event. Yeah. I guess you have already seen these slides. And I will just mention that we have a coming event on the 7th of November, a collaboration with Women Engineering Leuven for a IEEE Women in Power event, and you are all invited to join. But then I would like to thank EDGE, the new Transmission Competence Hub that was recently funded and that our professors actually funded for sponsoring the event. And you will have Professor Ergun giving an introduction and a short comment about it.
Given the time, I'm also going to keep it very, very short. So, yeah, EDGE stands for the Energy Transmission Competence Hub. And what we are actually trying to do within this competence hub is really future-proofing electricity networks. So we really want to be able to see more and more high-voltage DC connections and also more underground cables in the future. And we actually see there 3 ways forward. Basically, the first thing is something that we are already doing for the past so many years, investing more in research and keep doing the research that we are doing. But we are actually also in the process of setting up an industrial partnership program that is going to allow us to also work much, much closer with the industry and actually bring our research also closer to the application at some point in time. And one of the missions of EDGE is also to develop workforce and also offer training courses, for instance, for professionals working in some companies as well. And if you would like to get some more information, check out our website. And obviously, we are also always looking for new people to join our, I would say, very, very young and dynamic team, except myself, to join our ranks. So also for that, please check the EDGE website. And without further ado, I think we can start with the actual symposium. So today it's all about underground cables and also submarine cables. So first we are going to look a little bit into the life story of high voltage cable projects. So we are actually going to see from start to the end how such a project gets realized. And such cables are usually also installed in very, very harsh environments. So we are also going to see actually how this is practically done. Obviously, these are also expensive, but very, very useful assets. So we have to also take very, very good care of them. And one of these things is also to be able to monitor them. So we are also going to have a presentation which is going to dive a bit deeper into the monitoring process. And then the last presentation will be basically from the user of the cable, eventually the transmission system operator, to actually share also their experiences. So with that, I'm very happy to introduce the first speaker, Thierry Capelle, coming from Nexans. And he's already in the underground cable world for more than 30 years, so he has a lot of experience. Although his master's is, I see, from aeronautics, actually, in terms of topics, so a little bit of a change. And he has actually held several positions at Nexans. And today he's the manager of projects and installation in the Belgian grid. But he has also worked a lot on the development of cables, but also high voltage, low sec temperatures, as I know. And he's also a very active member in terms of standardization around cables within the IEC. Thierry, the floor is yours.
Thank you. Yeah, so the project by itself is very difficult to explain you what the project is in 20 minutes, since most of the time this project will take 1, 2, 3 years, a lot of time. So it will be a very condensated image of what the project is from A to Z. And also because the projects are changing a lot these last years in terms of scope. So of course you know this type of diagram, what is a network, fortunately. But then it's interesting to say when we speak about high voltage project, where it stands for, where the high voltage project will be part of. And it is mostly in this part. And this is what we called generation and transmission. This is typically where the project will happen when we speak about high voltage project. But you have to take care about that, because you still have high power projects that you might have. You have certainly heard about superconductivity cables, which are mostly medium voltage cables. It's a high power link, but it's not high voltage. So sometimes a high power link can be in medium voltage as well. But here we will focus mostly on the high voltage cable projects. So the project by themselves and the difficulty of the project is not new. Here you have the first project we did in a tunnel. It was in a cavern. The first of you who found the Flintstones get a beer after the presentation. And it's typically showing the complexity, because we had to pull down a 425 kV cable inside a cavern vertically with sealing in and a transformer at the bottom of the cavern. So a project in high voltage can be very complicated, but it's not new. For us, it's a long experience, and already in the 50s, it was well known that these kind of projects were difficult to manage and with a lot of steps. So today, what is the difference? The difference today is, I'm frozen? No, okay. So today, when you look to the project today, it's an end-to-end approach. So it's going a bit wider than usually in the past. There were a cable, there were terminations to install, joints. Of course, there was qualification in the beginning, a design, but now there are additional parts coming in the design and the reflection of the project. So of course, you start with what we call the engineering studies. Any project start with that. It's starting on our side, it's starting on the side of the client as well, making also a lot of studies to know how to manage this project, and so to make eventually R&D if it's a new type of product to develop, and also to make the design. After that, you have to type your product, and the type testing is taking sometimes a long time, even some years. So once again, when you manage a project, there will be the question of the planning. We will speak about that. And of course, the risk management, because you are starting to build something new that you don't know, and you have to foresee that this will have a life expectancy of 50 to 80 years. Then you have to product it and to transport it as well. So even the production as well ask for most of the high voltage project a long track of records. You need to have experience. You cannot start a high voltage cable in your garage. So it's taking time to have this kind of experience and to rely on it, and to know how to manage the project globally. After that, you have the installation. The installation can be on the sea bed, it can be on the land, it can be combined, land and sea. You have both. And so you also have, when you put some sea cable, to put some protection on the cable, which is part also. It's not only a civil work that you have to install the cable in the ground, but on the sea as well, you have to protect it against anchors, again, different things. And so it will ask again a lot of disciplines that you have to put inside your project. Then you have at the end, once your cable is installed, you have during the life of the project as well the client that wants to monitor your link. He wants to know how does it work, what are the temperatures, what are the risks he could have in terms of asset management. Is somebody trying to attack the cable? You never know. It can happen more and more, such kind of things. Or do we have a thermal problem or something else? And then, of course, during the life of the life cycle of the link, you also have to continue to monitor, to inspect, and to repair. Because even a cable laid at 2,000 meter depths could be damaged by an anchor or by something else, and then you have to repair it. So this is the scope, I would say, of a project in its whole, and we will go through the different elements. If it works, I'm frozen. I have to go here. Okay. Yeah. So in terms of scope, you will see that the scope can be either on the land or on the sea. And the project more and more, as I told you, we are making turnkeys more and more, where you have to make interconnection between a sea cable coming from a country to another country, or from and crossing the sea, And at both ends, you have to put land cables, because on the onshore part, you cannot, of course, interconnect directly on the network. You will need converters, and then you will need AC links to go a bit further on the network. So the project can be quite wide. And so to start from the easy part of the project, let's start with land. You see already a lot of things you need to know and to prepare. You need the qualification to make a pre-survey to know how will it happen. You need to prepare, if you are making a turnkey project, you have to prepare all the civil works, the trenching works, the joint base. And I will show you some pictures. Sometimes the joint base can be, or the trenches can be as wide as 26 meters wide. So it's not anymore a trench, it's a channel that you have to put your cable in. Then you have to produce, of course, your XLPE cables in function of the voltage, accordingly AC or DC. And then all the accessories terminations. After that, you have to test it. And then eventually to add the monitoring. I will show you different types of monitoring, and then to make the maintenance of the link afterwards. In the new projects, most of the clients are not only buying the project, but the maintenance with the project. They ask you to continue to maintain the link afterwards. If you extend the scope, it's the same as the land, but you add the subsea. And you can find similar things. You need a cable, AC or DC. You will need the accessories, joints. You will also need a joint to interconnect the land and the sea cable, so called the transition joint. And then you will need as well additional things like the protections. I mentioned that, like concrete mattresses you put on the cable at some places to avoid that the cable could be damaged where you have anchors or ships crossing in, or other things. Even sharks are attacking the cables, just for information. So we have in some areas special weapon cables against sharks attack. And then you need something very important and additional. You saw it on the first slide. You need a vessel. We have people from the Yandenil today with us. And they will show you the importance of having a laying vessel. Because when you have a sea cable, you need a laying vessel. Otherwise, you are dead. You need that. And it costs a lot of money and a lot of investment and time to build it. So it's part of the project. First thing which is key is the planning when you start a project. Without planning, you are dead. Completely dead is key. And your planning will have to start from the early beginning on a macroscopic point of view. So you see here, it's a general planning you have with general dates. What you see, the joints, these are the sections you have on the link with the different joint base. Then you have to look at this planning in terms of resources. You have to manage the resources, having enough resources in terms of man-hour or man-days. Can be quite sometimes a lot consuming in terms of people. And then, of course, you will have a much more detailed planning that you will have to follow with all the different people working on the planning, civil works, structures, vessels, transportation. Everything has to be planned and to be on time with a given deadline and a critical path to follow. And when you have a technical issue, you might say, what is a technical issue problem in a project in general? Let's suppose you are making a drilling under a highway, and unfortunately, you are not going left but right. You have to restart. This could kill your project for 1 month. You have 1 month's delay additional just to make your drilling back again at the right position. So you are losing extremely fast the time when you have a technical issue on a project. If you are making offshore and you have bad weather, adverse weather, your ship stays in the harbor. You cannot install your cable. So, and then the counting money, the dollar money, the dollar counter is starting to increase extremely fast. So planning is key for many, many reasons. And in terms of resources, a subsea and land turnkey project can go easily up to 200 persons. So it's a lot of people involved, from R&D till installation and so on. Yes? No? I don't know why it's going. Yeah. So first the qualification. Here you have an example of a 525 kV DC cable qualification, and you see already that your project is starting with the need of a building like a cathedral. So you need a lot of money to build such kind of equipment, to install such kind of equipment, only to test the piece of cable with the terminations installed. So you see here it's a DC cable with 500 kV sealing ends. In this case, these are termination mostly used for laboratory purpose on the right-hand side. And then you have a dry termination, which is a GIS termination. At the bottom here, it's a GIS termination. But you see here the size of termination, we are speaking about more than 6 meter high termination. So you need a lot of room to make your qualification. And this kind of qualification can ask up to 2 years. So very long time. Yeah. So then you need a layout. It's good to have your cable, but what do you do with it? So you need a layout of your link. And the layout of your link requires to have information about the cables, the accessories, the link boxes for the cross-bonding of the screens or the earthing of the electrical continuity conductors. And then you need, of course, some additional points, like if you have optical fibers, you will have some optical fiber racks or things like that. You need special support, you need special techniques to install the cables in tunnels and so forth and so forth. But the first point is to have your image of the link to know what is at SAC. And also, you need to see on the electrical point of view, you see here we have a transposition between phase, and it doesn't seem not a problem, but if you do not manage that correctly at the right time, your jointers could mix the phases and make a reverse order of the phase, and then you have a small problem for letting your cable link working properly. So this is also an important step to know your scope. What do I have to supply? What do I have to install in my project? Of course, if you have additionally submarine links, then it's much more complicated. This is a simple one. Otherwise, I will need 2 screens to, to show you the complete scope when you have a turnkey project. Then you have, of course, you are requiring engineering and design. So having the idea of how to do it is good and what to do, but then you have to design more in detail your project, how it will be done in practical point of view. Because once again, you will have organization, you will have time involved, and you will have to be sure that you are aligned with the expectation of your clients, of the permits. Everything has to be aligned with the expectation of what the clients wants to be at the end installed and working properly, taking into account many, many parameters. In some cases, you have to build that in the middle of nowhere. You have to build tents to make your jointings. And I will show you later on how does it goes inside the tent. I will show you how do they do that inside to make the jointing of the cable. But you see the complexity already in terms of design starts to look at some practical points. It can be more complicated when you go inside tunnels. Because you are not only putting your cable subsea or land, you sometimes have to go under tunnels, and then you have to make additional studies. These have to be thermal studies, because, for example, a cable in a tunnel will heat up your tunnel, and some electronic systems that you have inside the tunnel will not work at more than 40 degrees. So you have to cool down your tunnel. So we also have to make sometimes thermal studies inside the tunnel, how to force the ventilation inside the tunnel to cool it down. Because otherwise the electrical equipment or electronical equipment will fail. We also have to make sometimes mechanical computation to see how the structures will behave in terms of mechanical resistance to a short circuit current. And so we have to dimension some structures with finite element systems to be sure that it's correctly dimensioned. And then we also have to cross-check the transport capacity. Not so long ago, we got a question from ADIA Network, a TSO, Belgian TSO, who asked us, okay, I have 2 circuits, 2,000 square aluminium and 2,500 square aluminium above each other, 150 kV. I need that many MVAs. Will it work? I have a doubt. And it was a real doubt, because it took us more than 2 months to recompute the power, admissible power in the link, the capacity in the link, because it was really, from a thermal point of view, quite tricky. And it's even more tricky when you have multiple circuits besides each other, because the standardization is not foreseen for that. So once you have 1, 2, 3 circuits in the standards, you find it. Once you are going to 10 circuits, if you do not have your own computational model, you fail. You cannot compute correctly the maximal ampacity you have in the circuits. So it's also demanding engineering and methods and programs that we have. Each cable manufacturer has his own computation program to dimension correctly the length. Now, if we look to the cable and accessories scope, so we have now a bit more information about the design. So how will it go now in terms of solution? And the solution will depend on your scope, once again. Are you working only on a land cable? Then you already have different type of cable possible. Is it an AC or DC cable? Is it aluminum or copper conductor or copper enameled? Is it even a superconductive cable? Why not? Then it will be mostly medium voltage. And then you have, of course, to be sure that you have the adequate accessories certified and you have the correct choice in terms of standardization according to what the client is requiring in his own specification. And even sometimes it requires to have special accessories, like you see here, for example. Yeah, this one you see, is the interconnection between a crosslink polyethylene, so a synthetic cable, and a paper insulated cable. So sometimes you have to crosslink two technologies together. The accessory has to be built, therefore. If no, you increase your bubble, you are going offshore. Most of the case in offshore wind, you have always a land part. So you already are doubling your problem because you have then to multiply the different type of cable by adding some subsea cables together with your land cables, and of course you will have to interconnect them. If you are going even further, then you have to go to the interconnectors, and then you have the long links that you have to be done also AC or DC. And once again, it's increasing the bubble of activity and the number and the complexity. In terms of cable production, I will go very fast on that. It's just showing you that a cable seems simple, but it's not simple. The technology is requiring to be able to make the conductor with Millikan, so multi-segmental conductors for AC, for example, to manage the XLPE, which is totally different between AC and DC. This is not the same raw material, because in DC you have the space charges problem in your insulation, creating other phenomena you have to manage. Then the screen, different type of screen, also depending of the client, can be copper screen, aluminum wire screen, smooth aluminum, laser shielded, and laser welded. And then for the submarine links, you also have the armoring on the cable. And anti-damping system you also have on the cable. Many different materials to manage. And also, in some occasions, you also have to manage the fire withstanding of the cable, since you are sometimes land inside a tunnel. The cable is done, you have to test it. The story is not yet ended in your project. The time is still running. You still have to manage that the cable is 100% sure. In the cable industry, each drum, each centimeter of cable is tested. We are not making a random testing. We are making 100% of the test on all accessories, all cables. Why? Because if we don't do so, if we have a breakdown, it will cost 10 times more than what we have produced. So very important to test all this. A lot of tests, electrical test, non-electrical test, electrical characteristics, physical characteristics, water tightness characteristic. If you have a cable, even the ground is tested for water tightness. And also, of course, when you make it subsea, the conductor itself is watertight. And so you need that as well. And then you have some sampling tests like impulse. So you make a lightning strike on your cable system, cables plus accessories, to check that everything is fine. Then you have to transport it. Your project is still not on site. You are produced, but then you have to move it. You can move it for the land cable mostly by truck. This is what the most common manner we use to move the drums, because the size is not that big, even though some drums can have up to 6 meter width, because the diameter is blocked by the road limits or weights. So depending of the type of cable and the maximum length we want to put on the truck, we will go to longer and longer or wider and wider drum, because the diameter is blocked to 4.5 meter. This is the maximum gabarit we can use. And then we have to lose time, because even the cable is produced at day, you have to wait the night, because you need to transport your drums. And you do not need to transport one drum. but 3 drums, because you have 3 phases. If you have 2 circuits, 6 phases. Imagine 6 trucks on the road at night with pilot cars on the beginning and the front and the back, just to bring your cable on site. So once again, time consuming, very slow travel time, and so it's demanding, of course, with the ships as well. A vessel is taking time, and the big advantage with the vessels, with the laying vessels, the cable is on it. You can easily put 80 kilometers of a cable when it's not too high voltage on such kind of ships. After that, you have to install it once again. You are not really now in the operational phase. You will install it. So you have the laying vessels to install the cable. Of course, it will be via the ship that we will unroll the cable directly into the sea. And when the cable arrives on the seabed, we have remote of the vehicles that will open the trench at the bottom of the ocean to be able to protect the cable by jetting. So it's a hydrojacking who will open the trench and then close the trench afterwards to protect your cable. Then we can put concrete slabs when it's necessary on the cable to protect it from damages. You arrive then on shore, and then you are making the same with the land part. You have to unroll your cable to pull it in the trenches. You see here it's a 4-circuit trench in 380 kV, or partly internal. And what you see here is what we call the snaking. It's just to compensate the longitudinal elongation of the cable when the cable is heated up due to the carry-on of the ampacity. And then once you have done both, you have to interconnect both of them, if it works. No. Yes. You have to interconnect both of them with a transition joint, which is mostly on the shore. So here there will be an interconnection between the land cable and the sea cable. Here it's an easy case, but sometimes you are like in France. You have in front of you a big wall of concrete of rock, and you have to dig in and then to go up. And so it's creating much more complexity in your project, because then you have to withstand to mechanical forces, because you have to put your cable vertically at some point. Then you have to joint it. Once the cable is laid, you have to joint it. So you need special techniques. To joint your cables, you need, for example, like you see here in the picture, a TIGMIC system, because we are using in this case, a copper enameled conductor. So it's a conductor that gives you 15% more ampacity as compared to copper at the same diameter or cross-section. So requiring special welding techniques. And then the sealing ends as well. You see that sometimes the size is quite huge for the people to manage. So we have to manage not only the electrical part or the mechanical part of the installation, but also the safety part, because of course all these jointers have to work in difficult environment, and which can be extremely dangerous at some points, and namely when they work in the substations, because we have the connection bars live. Once your job is finished, you have to test it, because you have made a cable tested in factory, accessories tested in factory, but you are not sure, because the people has put his hand on the joint and termination, that the guy has made his job correctly. He might have made a fault. So once again, we need to bring systems, electrical system and electrical injection system, to make the final, what we call the SAT, the site acceptance test, to cross-check that all the electrical parameters of the cable, insulation, outer jacket, everything is okay. And if we have optical fibers in the cable for data sensing, for example, or for temperature measurement of monitoring, we have to check that the fibers are intact, in good state for any fiber. So this kind of trucks doesn't limbs, but from the left-hand part to there at the end, it's a curve photo, but it's 60 meters. So you have to bring trucks and bring 60 meters in a substation of Elia, managing all the risk with all the other equipments that could be surrounding. Here we were lucky because it was a green field, there was nothing connected, but sometimes you have to take care of other already connected systems. Now your project is finished. I told you, and I have somebody else that will speak about monitoring today, but just to give you an idea of different monitoring you might have. So we can use the optical fibers we have inside the cable to monitor temperature, vibrations. We can use as well some partial discharge devices, what we call HFCTs, high frequency current transformers, to measure the partial discharge on the cable accessories. We can also make the checkup of the screen current we have in the screens, just to see if we have something happening on the screens. Namely, for the C cable, it's very useful. If you have, for example, a cross-bonding inside your joints, to see that the cross-bonding is still working, otherwise you have additional losses and unbalancing of your link. So all these kind of things today can be checked by a lot of technical devices that we include inside the cable to make all this system. And then, of course, you need to buy and to install the related test equipments. Once you have done, you are almost done, you still have now to recollect all the data. You have a package of data, and you have to manage all this package of data to know what will I do with that. Then you have to make analysis. And why do you have to make analysis? Because your system is interconnected with other system, can switch to an N-1, you are losing one element on the network. How will behave your circuit compared to that? How much time do you have before switching out the link because you are overheated or things like that? So all this type of platforms that you can have today live on the web device and web application, they are giving you exactly the monitoring of your link with all the technical devices you put on them. You are also connected with specialists, so now you have hotlines. So if there is something happening and you don't know what to do, you can call them and to say, okay, I have a problem, I have a decision to take, what can I do? Does it make sense what I see practically on my system or not? How can I correct? And so there are trainings for the operators for that in such a way that they can analyze the data, collect the data all along the life of the link. And so now you have almost finished your project and hoping everything will run smoothly. And now you are at least relaxed. You are finished your project. Thank you. Yeah.
Thank you very much, Thierry. I think you had a very, very difficult task to sort of fit everything into a sort of a time lapse of 25 minutes, but I think you did manage it well. For the sake of time, I'm going to allow maybe one quick question, as we are also going to have a panel discussion afterwards. So any burning questions for Thierry for the time being?
Most of the time, when the cable is installed, it's most of the task of the network, so the TSO manager. You will see if really he sees something happening wrong. However, we will call if he sees something wrong. I will give you an example. On a link here in Belgium, in the south of Belgium, it's one of the feeder for the TGV line going to Liège. We were called one day by the TSO saying, okay, with my monitoring system, I see a hot point. And when the first question we rose is where? And he said, close to a joint. We say, this is not good. And so we were on site very fast because we thought there was a starting of a defect, because when you have a joint heating up and you see it with the thermal monitoring on your system, of course it will give you an indication that something is going wrong somewhere, or possibly wrong, and could go even further wrong. And when we arrived, we laughed a lot, because you know what happened? This hot point was only created by a farmer putting a lot of, mesh on the field, and it was really a mountain, more than 4 meters high, and it was creating a hot point on the cable. And we found that the cable was still in good position, because we were only at 95 degrees Celsius at the core, but we were quite at the limit. So this is the kind of things you might see, and the TSO will call us. Most of the time, our main task in terms of testing will just to check that the main insulation is in good shape, the outer jacket is in good shape, that we do not have any permutation of phases, that for example, if we have surge voltage limiters, they are correctly installed in good shape as well. So this is where our task will finish. If there are other analyses like frequency analysis or other things to be done, it will be most on the site of the TSO. And the reason why is the confidentiality, because we are not the owner of the network. And as soon as you touch to such kind of information, you touch to the confidentiality of the network, can be strategical. And so most of the time we do not have access to such kind of information, except if we have a problem. A few years ago, we got a problem on terminations, and we had to make a lot of studies with FTT transformation and so forth to understand what was happening, because one of our accessories was failing in transient. And we had really to understand why these transients were damaging the accessory. And it was part of our design that we had to adapt, and part of Elia network that they had to adapt as well. So then we work hand in hand in partnership to understand how to improve. Did I answer?
Yeah, thank you very much, Thierry. Maybe we can have a quick applause. And yeah, as said, we are going to have a second discussion afterwards as well. With that, it's a pleasure to introduce Dries Huygens from Jan de Nul. And he's a seasoned electrical engineer in high voltage substation and equipment design. And he has actually 2 master's degrees, one from the University of Ghent in automation and one from KU Leuven, Master of Energy. And he has been also an electrical team lead globally in offshore projects. And currently he's also the interface manager for the modular offshore grid 2 project, or the Princess Elizabeth Island project, I suppose, where he manages the landing design of cables, high voltage cable design, type testing, CPS design, and interface management. Dries, please, the floor is yours.
I'll first see if it works. Yes. Okay, thank you for allowing me to do this presentation. Also, thank you for making already a good introduction on how a project works. That makes my life a little bit easier. I work for Jan de Nul. Jan de Nul has 4 main services that we are doing. We are doing marine services, offshore services, civil activities, and environmental activities. I am myself from the offshore department, and I will focus more on that. In Jan de Nul, we are with 7,500 people working all around the world. We have 96 nationalities, 400 projects, so a lot of things to do. And mainly, we are working for the offshore services, of course. The offshore department, how we call it ourselves, is actually we're constructing the energy transition. Within Jan de Nul, yes, perfect. Within Jan de Nul, we are doing several things where you not always think that Jan de Nul is executing these type of works. We are building hydrogen plants. We are installing, of course, wind turbines and jackets and monopiles. They're also laying cables, laying land cables, building substations, towing floating equipment. We're building an island. It's a little bit small over there, but it's also there. We're doing stabilizations, and we're installing substations and also solar panels. So many things that you are doing. I'm from the cable department, so I will focus, of course, on the vessels from Jan de Nul that are doing the cable laying. We have 5 vessels. The first one is the Willem de Vlaing, which is a smaller vessel which can be used to install cable on a very low draft, meaning that we can enter near the beach. So that's quite an exceptional type of vessel. And then we have the Isaac Newton over there, the connector. And then we have our very 2 big vessels, which we are building and we will deliver in 2026. And it's the Fleming Jenkins and the William Thompson, which is linked to the first installation of the submarine cable in 18-something. It consists of 3 carousels, with 3 tensioners, of course, 2 ROVs. ROVs are used to monitor a cable below in the seabed. It has a 2.5 megawatt-hour battery for a battery to have. If you're using a tensioner, you have a current peak, and you need to. This can catch the current peak, and it has an ultra-low emission vessel. Has anybody an idea why we are using 3 carousels? Because it's actually quite exceptional. Do you know why? Given an idea, it has a link, something to do with DC. Somebody knows?
Bipolar.
Indeed, yeah. The reason why we have 3 systems, indeed, because we're installing a plus, a minus, and the metallic return all at once, which is actually quite, it's the only vessel who can do that at the moment. So that is where we try to make the difference. You might think, what does an electrical engineer do on Jan de Nul? We are, of course, just an installation company. But what I think the reason is why we need people in electrical engineering in Jan de Nul is because there are many interfaces to our project. As Thierry explained, these projects are now getting bigger and bigger. We need to do more and more stuff, and all these things cannot be done by one company. We always need a cable manufacturer. We need Marlinks to do the DTS. We need other parties to do these, to do civil works, to do installation, to build an island. So there are so many interfaces that are causing a project to be more complex. Myself, I'm working on the energy island. Here you can see the energy island being constructed. This is a sliding formwork. This is one of the caissons. And before I want to go more into detail, I want to, because a lot of things have been said about the energy island lately, more expensive raw materials and higher interest rates, making North Sea energy 1 time more expensive. The costs of the energy island are rising. Already too small for Tine van der Straat and her ambitions. The Danes do not want the DC cable anymore. And Elia awards contracts worth of 1.5 billion to connect the energy island with the mainland. And then, I think it was last week, Belgian Island risks costing 7 billion euros instead of 2 billion euros. It bothered me a little bit that it came on the news, because I think you're comparing apples with oranges. If you do a very quick check, then you can actually notice that the 2 billion is just for the AC system and for the energy island. So the TED and all the other people made actually a wrong conclusion, because the 7 billion also takes into account the HVDC system. So just to put things more in context, it's not always that easy. The other thing I noted is that the TED should use not always the same drawing on their publications. Also, Tina said, if anyone puts everything on hold now, it's also putting stable and secure electricity supply at risk, which I think is also true. Even though it costs a lot of money, I think we should still do it, because we are now at a turnkey point. The climate change is real. What we can choose is either to pay for the energy island, which might be a cost right now, but all the other costs that we are facing, or we may face due to not doing the energy transition, may be so much more higher. You can see it here. We are right now, we are over here, and there are a few options. Either we do something about it, and we can reduce the temperature change to and limit it to be not too high. But if it's too high, the impacts will be quite huge. Another thing I wanted to highlight here also is that although we are doing an estimation of the costs, because of the interfaces, it's always too difficult. I suggest you also can read that book. It's not only the energy island, it's also Oosterweel, who also starts to increase in money prices. So it's just to put things in context. I'm drifting a little bit off, so I will go back to the energy island. The energy island consists of a lot of cables that are entering to that island and are actually connecting and transmitting energy from the wind turbines to land, or also being sold to the UK, which is then the Denmark, which is then the Triton link, and Nautilus, which is then the UK. Now, the energy island then consists of 96 cable landings. So you have to imagine that on that island, which is I think 800 to 400 meters, and I'm not entirely sure if it's correct, but all these cables needs to be routed on that island. And that actually creates a complexity to the complete energy island. And the energy island should be used to be this energy hub. Because if we're not having the energy hub, and if we can connect these cables on that island, we just have an island. So we can use it for retirement or something, but the energy scope is actually quite functional, so it's quite essential. So that needs to be taken into account. And for a submarine cable, and Thierry already explained a little bit, I see actually there are several interfaces. So you have a thermal impact, which depends on, for example, burial assessments, or depends on the neighboring cables. You have the electrical scope, of course, which is to size the cable, where you are probably very good at. Then you have the magnetic impact, as I explained before. Putting the plus and minus together is most of the time essential to for an environmental point of view, to avoid impact of magnetic issues. And we have the mechanical issue as well. For the mechanical issue, I would like to focus again on the energy island. Here you can see the cable landing. This is a cross-section of one caisson, where you can see a J-tube, which is installed on top of the scour protection. Now, what is different compared to a usual monopile or a jacket is that here you have a wall. And there on that wall, you have that wave, and the wave comes in, and it stops. Whilst when you go to a monopile or a jacket, what happens? The wave comes into the monopile, it opens, and it closes again. So here you have a huge energy that is impacted on that cable, so you need to protect it. The cable needs to be able to handle all these forces, so that's also part of a design for a submarine cable. Not only that, also the scour protection here, that are rocks that are being installed to make sure that your island is stable, are very, very big rocks due to that high amount of force that is impacting on the island and also on that scour. So these rocks have a tolerance of plus minus 1 meter because they are so big, meaning that actually to enter your cable, because you don't want to have any free span over here. Free span means that your cable is not touching anything. You want to avoid that. Why? Because due to that high force will also impact that, that part of the cable. And here, to have that cable landing, we have installed a J-tube with a dual entry, because we want to minimize the tow protection depending on, to minimize the free span depending on the height of the tow protection. I don't know, yeah. But it's not only that, we also need to, for instance, this is one of our vessels, where here you can see how we install the cable. So we use a tripod where we install a winch and we pull the cable into the J-tube, and we connect the cable to it, which is on the vessel. Here we need to monitor cable tension, pull-in tension, back tension, the minimum bending radius, and the maximum sidewall pressure of the cable. And this is all done in Orcaflex, so it's a finite element modeling. So to do this pull-in, we need to do a complete finite element modeling. But you can see here, even if we put it in, if we would not protect the cable over here, we would drag it over these 3 to 6 ton rocks, which would damage the cable. So we also need to foresee some kind of cable protection system. And it was never explained to me during my education what a cable protection system was, but it's actually really important. It's something, because this part is actually a point of failure in your cable next to the termination. This is also an issue, because here you have these fatigues. So here you have your entry okay, this is a monopile. You have your entry over here, you have a free span, and then you need to do it on top of the scour protection, you need to bury it. But this part needs to be protected. And what do? We use a CPS. This is a small model of a CPS. You can see it later, you can have a look at it later. So we pull the cable through, and this we use, wait, here you can see how a CPS looks in big. So here we do it on the chute of the vessel. We're dropping it down. And another issue we are facing with the energy island is the 3 to 6 ton layer. The 3 to 6 ton layer causes actually because of their rocks are so big, you actually had a huge free span. The free span between those rocks is almost 4.5 meters. So we are on top of that, we also need to protect the cable. So we need to drop rocks on top of that as a stabilization layer. And the higher you go, so the higher you come to the surface of the sea, your forces will be more and more, and your current will also increase. So if this is a 3 to 6 ton layer, imagine what needs to come on top of it. Right now we're looking at 8, 12 ton rock bags, 16 ton rock bags, and they need to be, these CPS systems need to be able to withstand the impact of it being dropped down from the sea level, because we are not just lowering down easy, because that costs money, and so we might as well just develop it good enough so that we can have the impact. But also over a longer period of time, because this is polyurethane. Polyurethane deforms after a while, so also needs to be taken into account during the lifetime of the cable. This is yet to be solved. We haven't solved this yet. On the other side, so when we are pulled in onto the energy island, so now we are over here. We also need to, pull the cable in, and we need to bring it to the AC substation. The AC substation is located more or less over here. So you have to imagine, if this, let's say this is 400 meters, this is we have entered a cable here, then we need to route almost, let's say 200 to 250 meters of submarine cable onto the island. I think you can imagine that is way too hard, because a submarine cable has also a twist. So you're twisting your course, so you need to untwist it. But untwisting 250 meters of cable is almost impossible. That's why we are, okay, I haven't drawn it yet, but here there is a joint. There will be a joint where we have a land cable from Nexans, and we will have a submarine cable from us with a joint in between. But what I want to show here as well is that we need to be able to route this cable through. So this is also an interface, because our energy island is built by a civil department. So our civil department builds that island, but they are not always taking into account the necessity of a cable contractor, or the necessities of a monitoring company. So that is all these interfaces we are trying to cover, and we're trying to take into account, and we're trying to solve it right now. Also, it's actually a stupid thing, but as you know, we want to have the electrical system to be double on each side, to be earthed. But if you put your joint over here, that means you need earthing points. But concrete, okay, although concrete is a little bit conductive, it's not, the area requests 0.1 ohm. So yeah, we need a cable for that. So there needs to be a cable installed into this layer, which is the top slab, where we install a cable. We have the earth points over here, such that we can install our joint on this location. Not only that, we want, because we are pulling in a cable over here, but as Thierry already mentioned, a joint is very complex, and is usually the point of failure. If you have a failure into your cable, 95% of the time it's the joint. So what we do is we want to foresee a room for a retermination, meaning that we have to pull an extra cable to make sure that we can terminate it, and that we can re-terminate it, so we can do it once more. And that is also a very complex situation, because you want to be able to have that space available. And thinking about this picture, 96 cables, they all need to have a joint in this area, and they need to have a overlength, sufficient overlength for retermination on two sides, on the land cable, on the island cable side, the cable between the joint and your substation, but also the submarine cable. So that creates complexity, which we need to take into account, and we need to solve. Janel is not only building the island, we are also installing a cable at a consortium with LS Cable. It's a Korean company. I brought the cable of Hollandse Kust, so you can have a look at it later. And as Thierry already mentioned, we always want to protect the cable. Protecting the cable, we usually do indeed by either installing rock mattresses, or we can bury the cable. This is a trenching tool. This is the Moonfish, where we can trench up to 5 meters depth with a sword. So the sword is cutting in cutting mode or in jetting mode, which is actually putting a high amount of water into the sand so that it liquefies, and the cable, doing its own weight, drops all the way to the bottom. But that creates complexity, because the deeper you go, the more thermal, the higher the thermal impact will be. So that needs to be taken into account. Also, your cable needs to be able to, with the cable parameters, the mechanical parameters cannot be breached, such as the MBR. So all needs to be taken into account when we are designing this cutting tool or this trenching tool, because yeah, the cable is actually the vital system of the energy island. I mentioned before that we are actually, that for electrical sizing, it's not only electrical sizing of a cable, it's also something what I was not always explained during my education. It's also the thermal sizing. I would even say that the thermal sizing is even more relevant than the electrical sizing. That is what we are also doing on the Null. This is, for example, a connection between, let's say, mainland Belgium and the energy island, where we also have 3 connections. We have an offshore field joint, because we need to do 2 first-end pulls. The first-end pull means that you're taking one end of a cable and you're putting it into the termination, then you're laying it, and then on the other side you do the same, so you wet store it then. Over here we wet store it, meaning that we are putting a seal on top of it and we're dropping it into the sea. Then on the other side we're doing the same, and when we arrive here we make an offshore field joint. But we have made 3 sections over here. Our cable is made out of 3 sections. The 3 sections, why we have done that? Because the thermal behavior or the burial assessment that is required on each of these lengths is different. So here, for example, at Scheur is what we call it is a very, very thermal issue over there, because we need to bury the cable very deep, because the vessels are passing by. Here we have a higher cross section. Over here we have the J-tube. The J-tube is usually also a hotspot, because you have air trapped inside the J-tube. Air trapped inside the J-tube means that your air, you can always heat up. It cannot cool down. It cannot be released. So there you also have a higher temperature. So we are doing this by using thermal sizing, and not only that is the issue. Also, what also managed by Thierry already is that if you put 3 cables next to each other, you will have a thermal impact, and that is not described in any standard, or not enough described in every standard. It depends also if you're then doing a finite element model like what we have done over here. You can notice actually if you're putting 25 meters apart from each other, it's actually already okay. But these things need to be calculated, and it's not in line with the standards that we are finding right now. So these things we need to do to make sure that we can optimize our complete cable, because we want to reduce the price of the energy island. This is also part of it. So that's what we are trying to do here. I want to end the presentation with, I made it with ChatGPT. I asked him to make a drawing of electrical interfaces with processes and so on, because what we think is that a project which is that large usually comes to handling interfaces very well, because it's these interfaces that are causing the delay. It's not the inflation, as the Tate mentions, it's the interfaces. The interfaces need to be managed well, and that requires a process and needs to be set up correctly. If you have many interfaces, many parties who are working together, you need to make sure that they are all aligned with each other. You can use an interface matrix for that, but you also need people who need to look at all these interfaces closely and which are responsible for it. Otherwise, it will go wrong. Okay, that was the end of my presentation.
Dries, thank you very much. I really appreciated your presentation, where you sort of gave a little bit the broader picture and actually put everything into perspective, because I do appreciate your point. Also, if you're only looking at the cost of expansion, but you're also not necessarily looking at all the benefits that you're going to get out of that, then you're only telling one part of the story. And, having a cleaner energy system will not happen for free, and everyone who is thinking that this is going to be cheap is, I think, a bit delusional. But also on top of that, I really appreciated that you showed this, I would say, rough life of a cable getting installed with everything that is dropped on the cable. So I think it's, yeah, it was also for me very interesting to hear. Before we move to the break, do we have any burning questions for Dries at the moment? Oscar?
If we have to follow IEC 60267, then we do that. And that is what the client requests. If the client requests to use finite element models, we do that also. It's based upon what we are requested to do. I do admit that IEC 60267 is a little bit conservative, because if we're doing calculations using finite element models, usually we see that the temperature is lower, or the core temperature, so your core section can be decreased.
And can you convince the clients to reduce?
It depends on the contract. So, for example, in the latest contract, it's written that we may use finite element models to prove our case, and usually, if there is a good technical description why we are doing stuff, then mostly they are okay with it. We need to have a good background story why we are doing stuff. And then
so let's continue with the next two presentations. Yeah, it's also a great pleasure actually to introduce Simon de Rijke, who graduated from KU Leuven, and for his master's degree, and also did his PhD in electrical engineering in 2014. We also shared an office with Simon around that time for a couple of years as well, so it's always a pleasure to have him here. Between 2014 and 2020, he has worked for Nordex Acciona on grid integration, and then also at ENGIE Laborelec as a power network expert. And now he's an R&D manager at Marlinks, developing DTS and DAS techniques for monitoring submarine cables. Simon, the floor is yours.
Thank you, Hakan. It's indeed a pleasure to be here after 10 years, to be back in the aula. Let me try to kick off this presentation and, yes, start the slides. I will be talking about monitoring solutions, and I will set a few boundary conditions. So I will mainly talk about optical techniques, but I'll give you a bit the perspective in the first slides. But I was happy to hear Thierry and Dries talking about monitoring systems and about DTS and DAS systems. So at least you heard about it by now. Did anybody hear about distributed acoustic or temperature sensing before today? You can raise your hand. Just a few? Okay. So we'll take a few steps back when introducing this technique. So why do we monitor our cables? It's said a few times, it just costs a lot of money when your cable fails. So you really want to avoid your cable to fail. But unfortunately, in 80% of the 80 claims on offshore wind are related to your cables, or its accessories. I believe it includes accessories. It costs a lot when your cable fails, and it takes quite a bit of time. These are average numbers, I believe, from Ore Catapult. 60 days on average for repairing a single export cable. It will cost you millions of euros. The cable costs about 15% of the initial wind farm capex cost. I don't know whether that number still holds, but it's quite significant. So it really matters that you keep an eye on your submarine cables. Now, I know the title was about monitoring techniques. There's quite a bit of monitoring techniques out there. Jerry already mentioned some of them. Partial discharge is one of them. surveys, MBS surveys, sub-bottom profilers as well. Current sheet monitoring mainly on land cables. You have a whole bunch of fault localization techniques. Time domain reflectometry is one of them. It's the most commonly used. But I will only talk about the optical techniques. And in the family of optical techniques, I will mainly talk about distributed temperature sensing and acoustic sensing. There's a few others, but those are, let's say, the most, I shouldn't say promising ones, because there's a few other ones as well, but you clearly see them coming up in the cable world. So, what about DTS and DAS? So DTS stands for distributed temperature sensing. DAS stands for distributed acoustic sensing. Just a small picture. Imagine this is an interrogator and it sends out a laser pulse. And it sends it out through a fiber. And this fiber is, if you look very closely to Dries' cable lying over here, you would see this picture here. And you would see that there's a fiber optic cable embedded. It's mainly used for telecommunication purposes. Some cables have specialty fibers for monitoring, most of them don't. So it's standard telecommunication fiber, but you can use it for monitoring. So you can send your laser pulse through this fiber, look at the backscattering of the light, and the way this backscattered light changes tells you something about the temperature. And because the time of flight principle tells us where it effectively the temperature changed or the acoustics. So we actually know the temperature every meter or every 2 or 3 meter, depending on the spatial resolution, along a 50 kilometer cable. So you know the status of your cable real time at any position. And I've added a picture here on the blackboard because it's not just one cable in most of our setups. So we have one interrogator on the offshore substation. From the offshore substation in a typical wind farm, you have an export cable going to the land. And then you have your inter-array cables, as they call it. And they're organized by strings. One string goes to, I don't know, today, 6, 7 turbines, more or less. The interrogator looks on the fiber on the first string, looks at the backscatter, and then looks to the second string, and then to the third string. So he, in the end, he measures all fibers, all cables, not at once, but almost at once. So sequentially, or in some setups, we do it simultaneously as well. So you know the status of your cable in your complete wind farm. What do we do at Marlings? We don't intervene in the cable. We just take the fiber as it is there. There's other companies, as we heard, who are very good at doing this. We do hook up the interrogator, servers for processing the data, we set up applications, and we make models. And from those models and all of this, we provide insights to the operators of the cables, and we try to tell them what the status of their cable is. And this is a very famous statement of our founder and CEO, the expensive box syndrome. So what we typically saw a few years ago is that DTS and DAS systems were installed, but they were not effectively used. So they were just standing there and they were only used when something happened. And then the problem was, how do we get to the data? What does the data tell us? You can tell the state if something happens along your export cable at this point. You will know the geographical coordinates of your cable, but you have to align your fiber with respect to those geographical coordinates. So you have to translate what you see on your fiber to geographical coordinates. And if you have to start doing this when the failure is already there, the time is ticking, the clock is ticking, and yeah, you're losing money. So it makes sense to do this on beforehand. So that's what Marlings does. Just in a nutshell, we do the installation of the interrogators as well. We hook them up to the fibers, but mainly we're data analysts. Some of us know a bit more about power cables, of course. Checking, yeah. So I already explained that I will be mainly talking about DTS-based solutions, temperature, and DAS. And there's a few products that are mentioned in those two categories. Now, there's a few optional solutions. CCMS stands for current. It should be current screen monitoring. We also have termination monitoring. That's also based on an optical technique, but with fiber Greg ratings. I won't go into detail there. But there's a few other things that we do besides DTS and DAS DAS monitoring. And we mainly work on, we mainly monitor submarine power cables. There's a few projects where we do monitoring on land cables, but we mainly focus on submarine cables. So DTS. The first and the easiest what you can do with your temperature is real-time thermal rating. I will just jump over a few sales slides and just go to the technical details. In the end, I'm an engineer. So what does our RTTR tool effectively does? It gives you the power cable core temperature. We can also forecast a little bit. So if an operator would like to know if I increase the power that much for 24 hours, what temperature will I see? So that's also possible. That means you can also calculate the time when your cable will effectively overheat. But in essence, you calculate the power cable core temperature and you use your electrical and thermal cable properties for that. Of course, the location at the point where you're calculating it. You also need the current and of course the fiber temperature. We do finite element simulations, but they're way too heavy to run them real time. So we use them to make a thermal ladder model, which is something like this. Which you can solve very easily in real time. And now coming back to the IEC and a few questions in that respect. IEC also prescribes a thermal model of a cable, but the problem with IEC is that those nodes in this thermal ladder model, TA is the position of the this is our model. This is the model we make in-house. And the most important point is this one. It's the point where the fiber is located. So it's this one here, this one in the middle. But IEC also made a thermal ladder model like this, but they don't have a node for the fiber. They only have a node for the core, the screen, I think the armor, and then the ambient, and maybe there's one more, but they don't have one for the fiber. So the problem is, you can use the IEC model to make a thermal model, but it doesn't give you the temperature at the fiber. So you cannot start calculating the core temperature if you don't know the temperature at the fiber location. But if your customer asks you to use the IEC norm anyhow, you just make wrong calculations and you might overestimate, in most cases underestimate, the effective temperature. And that's not something you want to do in your operational phase of your cable. You just want to know the effective temperature that is there. And then we translate it and display it to our customer in a dashboard. There's a few other features to this dashboard, but I think that will bring us too far. Depth of burial. What's the most efficient way of protecting your cable? I heard mattresses, but most of the time they bury the cables. What you want to know for the lifetime of your cable, is my cable still buried? And if it's buried, how deep is it buried? Is it buried 20 centimeter? Is it buried 1.5 meter, which is more effective? So we have a tool that calculates the depth of burial. Now for RTTR, if you go back to the thermal ladder model, you just start with your fiber temperature measurements and you calculate the core temperature. So the only thing you need is a good cable model. Now for depth of burial, you need a bit more. You also need a soil model. So what we do is we calculate the temperature at the fiber location, at this location, assuming different possibilities for the soil model. The cable model we just know. It has a data sheet, so we know it. But the soil, it can change over time, it can change along the distance of the power cable. So we use quite a bit of combinations, and then we end up with quite a bit of combinations or possibilities of the fiber temperature at the fiber, and we compare it with the real measurements. And the one that gives us the best fit, that tells us which soil properties there effectively are, and what the depth of burial is of the cable. That's our depth of burial model in a nutshell. It's a bit more complicated, so it might not ring a bell, but we will need a bit more time if you would like to explain this one. In the end, you end up with a depth of burial value for every position along your cable. So for instance, this cable here at distance 9 kilometer, it tells you your cable is buried 1.5 meter. And in this case, they made a comparison with another technique, with a sub-button profiler, just to see if we have comparable results. Here's a few other examples where they compared a traditional survey with our model for calculating the depth of burial. This is something very typical. These are dunes, so the depth of burial changes quite rapidly. Just a few comparisons, and this also ends up in our dashboard. Then the new kid on the block, DAS, distributed acoustic sensing. So DTS generates data in the order of magnitude. So the order of magnitude is gigabytes, roughly. But DAS is generating data in the order of magnitude of terabytes. So it's enormous. So there's an example here on the slide. So this happens with sales presentations. It's not possible to interrogate your cable at 2000 hertz over this length, because you don't wait until the light is reflected. I think the limit is at 49 or something. So this is we should put 50 here. But let's just continue the discussion. This number will be a bit lower, but I can increase the sampling interval to 5 meter, and then I end up with 2.6 anyhow. So if we would sample our cable at 2000 hertz, so it means sending out a laser pulse and looking at the reflection 2000 times a second over 75 kilometer, with a spatial sampling interval of 10 meter, I have 2.6 terabyte on a daily basis. So impossible if your interrogator is on the substation. We haven't met an operator that is allowing us to transfer this data to the land. It's impossible. So you have to reduce the data locally, at least a factor 1,000, and then you can start talking about sending this data not to the cloud, certainly not for TSOs, but to a secure server on the land where you can do some more calculations. So the first challenge with DAS is, and still is, it's the vast amounts of data that needs to be reduced. Thank you, Hakan. So I won't go into the data pipeline, but I'll explain what you see and what you get by showing you some results from a field measurement campaign. And this was a field measurement campaign on a dynamic cable. So dynamic cables, they have quite a bit of free span. So it means they're subject to quite a bit of forces. Just to give you an idea, the distance from the cable from the hang-off here, this point, until the touchdown is roughly around about 200 meter, 190, 210 meter, depending on the configuration. And if you would sense, so if you would read your DAS recordings, your measurements, at this point here, somewhere here, where the cable is lying on the seabed, you would see something like this. And what you actually see is the wavelength of the waves. So there's hydrostatic pressure from the waves above. That's the first thing we see. So the cable is not moving yet. It's just lying still, but we see the pressure of the waves on top of it. Now, we go to 2 points more. This is the touchdown point. This is the Hock band of the lazy wave configuration. You can clearly see that the strain, because DAS is, and that's a bit confusing, DAS is, it's called distributed acoustic sensing, but in essence we're measuring strain, so elongation of the fiber. But because we measure it down to nano strain levels, you're actually picking up acoustics. So if you're talking in the vicinity of the cable, you can see it. So it's extremely sensitive, extremely sensitive. Here I'm showing 2 measurement points along the dynamic cable, so you can clearly see the intensity increases. If you go to the hang-off, it's even more. It's the fixation point, of course. You can show it in another visualization. It's better. Here you can see the waves in a heat map. And here you see much higher intensity. I played a little bit with the max and min values of the scale, so it looks a bit distorted here, and that's just because the signal is very high. And then you can start analyzing it in the frequency domain, and then this tells you quite a bit. It tells you which forces or which drivers are moving your cable and at which frequencies are they doing it and how intense are the movements. So I'm visualizing here a spectrogram along the distance of the power cable, and this is the frequency scale. You can see the waves, very typical, 0.1, 0.2 hertz. They're the main driver for moving your cable. But also the floater is moving at its natural frequency, and we could clearly see this at the touchdown point. It's like the floater is like pulling the cable. Some structural loads that the operator of the wind turbine didn't expect to see, so that's work in progress. Because of the time limits, I won't go into detail in all of them. I'll just explain a little bit about, I'll just go very briefly over them, just to show you what you can do with DAS and what we are all looking into. CPS systems, it's been introduced by Dries. A few years ago, Ørsted realized the cable fault was due to possibly faulty design in the CPSs. They were not stabilized, so they didn't have the stabilization layer on it. They had a warranty provision and expected, I believe it was 3 billion that they foresaw to mitigate all of these problems in their wind farms. It didn't end up that bad, but that raised quite a bit of issues. So one of the things we're doing is CPS monitoring. That's a rock dump, also mentioned by Dries. If you do a rock dump, you dump your rocks. If you dump them on the cable, it brings quite a bit of forces, and this is how it looks like when you look on the DAS without further analyzing. So it's very intense, easily to find. A bit more pictures. That's a case where there's actually no intrusion on the cable. It's a possible threat, yes, but it's not an intrusion. This was a vessel that was going over the cable, not touching it. So no fishing gear thrown out, just going over the cable. The dots you see, it's the AIS system that is obligated for most of the vessels. And the dotted line here is the cable trajectory. And what you could see is that the speed increased when it was sailing over the cable. And here you can see, when we looked into the dust and tried to find the vessel, we could identify it in time and in space. So this opens also quite a bit of possibilities for monitoring your cable and looking for possible threats. One of the reasons why they don't want, or why they are very reluctant in allowing DAS in the US, because you can potentially track submarines with it. They don't want you to be able to do that. Electric fault monitoring, not sure if it works. Yeah. Electric fault generates an acoustic shock wave through the cable. Acoustic, so we can detect it, we can see it. This was a small setup where we applied a fault. We applied different fault in different conditions. When you see the fault, you very clearly see an intensity increase on the DAS. So it's very effective in localizing and even pinpointing the fault. That's a bit more information. And the final one is environmental monitoring. If you speak in the vicinity of the cable, we can see it or we can hear it. If a mammal is doing this, a whale, we can certainly see it. So that's also possible. Earthquakes, also possible. This was an example of an earthquake, I think it was the Fuji Islands, not sure, that we detected while monitoring on a cable in the North Sea. Because an earthquake generates seismic waves, and seismic waves, you can pick them up with us. And this is where we are active at the moment. I think the list is more or less up to date. So we started in Belgium, I believe 2017, the Netherlands, but in the meantime we were also in Taiwan, in the US as well, and a few other countries. And that brings me to the end of my presentation. So thank you for listening.
Thank you very much, Simon, for the very insightful presentation. So next time you remember not to talk very loudly in the vicinity of cables if you have something to hide. Any burning questions to Simon at this time? If not, then I will ask something. Okay, Dries, please, yeah.
I have to reveal some details of what we've shown here. The rock dump was not on the cable here. It was next to it was another rock dump activity in the near vicinity of an existing cable. So it was not on the cable. But in the hypothetical case that we would be monitoring, it is from a practical, we checked it a few times, it's practically very difficult to do monitoring on the fiber optic while installing the cable, and thus while putting the stabilization layer, just because you're in a time critical phase of the project. Yes, of course. It could work when it's not energized. It's purely from, we try to measure, because it would be very interesting to measure the strain on the cable, what you can do with DAS. It's on the fiber, it's not on the cable itself, but you can deduct quite a bit of information from it while the cable is installed. But it's practically not very easy to do it. We once started a project as such, but we failed. Thank you.
And Simon, maybe also a quick question from my side. So with, let's say, the type of techniques that you're doing, would it also be possible at some point in time to actually have an estimation, for instance, on the lifetime of the cables, or for things like doing predictive maintenance and things like that?
Ultimately, yes, I think it's possible, but not at this moment. The reason, and we mainly get this question when talking about distributed acoustic sensing, because when talking about fatigue of let's take the example of a dynamic cable, they want to see SN curves. So how much do you move the cable at which frequency and which amplitude? The problem with fibers embedded in power cables today is they're in a loose tube configuration. You can see it on this cable as well. So the strain we measure on the fiber is not the strain the power cable is experiencing. And they're looking at tight buffered fibers, where the fiber is tightly embedded to the power cable. And then you could make estimates about lifetime much easier. But not today.
No, that's very interesting to know. Yeah. Thank you. Whoa. Okay, then we will move to the last presentation. And it's also a pleasure to introduce Johan Remé, who is a true power systems expert. So he has graduated in the year 2000 from the Free University in Brussels to join Elia. And he actually did a remarkable job of also pulling off a PhD while he was actually working full-time for Elia as well, which he completed at the same year as Simon. And yeah, said he's a true power system expert and is working with the analysis team within the asset management group of department of Elia. And he's surveying the AC high voltage grids, DC converters, wind power plants for short circuits, switching phenomena, I read here, power quality, harmonic stability, electromagnetic fields. And even, more exotic power system phenomena. I remember you did some studies for geomagnetic storms at that time. And in the years to come, you will also be spending a lot of time and effort on the design and conception of the electrical system for the Princess Elizabeth Island in the North Sea. And today he's going to talk about the practical issues that Elia is facing, also with respect to environmental considerations when having cable routes in the system.
Great. Hi. Just put my chronometer. I fear this little page of I can't already. Okay, good. All right, guys. So, the title of the presentation is Environmental Considerations for Cable Routing. So, with cables, you put them in the ground and you never talk about them anymore. So, how can there be any environmental considerations? So, we scratched our head and we found some which could be of interest for this night. And I hope this. Where should I pinpoint? Here? Oh. Okay. So, right. Mainly two topics. We start off with the onshore or the land cables, let's say, and then we drag this knowledge into the sea, let's say. So, impact of land cables. Imagine these are the cables between two substations, or even three if you want, buried on the ground. What possible impact could they have? And I would, let's say, compare them already with overhead lines. Of course, this is a cable symposium, but I will talk a bit about overhead lines. I can barely read the slides for myself. Of course, the main issue or the main topic for both of them are the electric and also the magnetic fields, and especially the magnetic fields, because electrical fields, you can shield yourself quite easily, but the magnetic fields penetrate everything, Also for overhead lines themselves, you got these bird migration routes, and we get more and more attention to this point, also for environmental institutions and so on. They say, yes, your overhead lines, they're really, really harmful for birds, ducks, geese, and so on, which would fly against these conductors. And we say, all right, we take it into account. We're not sure. We don't find these, let's say, dead birds on the ground regularly, but okay. Visual impact on the landscape, maybe that's a way or a driver to go underground, let's say. Okay, EMC impact on sensitive equipment. We know some people living just below overhead lines are with expensive, let's say, swimming pools and air conditioning and so on. They would suffer. Not quite a lot, but regularly we get complaints of this. So this can also be, let's say, in a more broader sense, an hazard on the environment. Also impact on short circuits and maybe a safety hazard for cranes. These cranes happen to once each 3 to 4 months. We got a crane in the overhead line provoking a short circuit. So if we exploit this knowledge already, what could be said about underground cables? Yeah, electric and magnetic fields, especially the magnetic fields. These will be, let's say, the subject of the slides later on. They got limited or no visual impact. Limited, sometimes you see a junction pit or some kind of little pole sticking out to say, here is our cable, but nothing more. Talk about later. Impacts on short circuits, yeah, and especially some safety hazards for excavators. Excavators, you know, they don't consult any plan, they don't make any appeal to whatever data bank, and I'm apparently switching the slide all the time. And they would just dig in our cables, which happens, yeah, more often than we would like. Yeah. So undergrounds are perhaps, to, let's say, environmental impact, the more elegant solution, but with a huge side note, which I come back later. Good. Every time you would, let's say, have a project and would develop a cable route, and you need to decide, how do I want to lay down, bury my 3 individual phase cables or cable phases. You could do it in a trefoil position or a klaverblad for the Dutch speaking. It's really fantastic. Yeah, the 3 conductors are so close to each other that you won't notice any magnetic field radiated from the cable, especially at some meter or 2 meters, because the currents provoking these magnetic fields produce each of an individual magnetic field, but they cancel out immediately because they are so close to each other. Remember overhead lines? If you would come with a field meter, you would only measure the magnetic field, also the electrical field, of the lowest conductor, if you would be immediately under. For the trefoil positioning, it's almost perfect. And we can do even better if you want to. But they're just glued one to each other, not with physical glue, but so close to each other that the heating of the current passing through, yeah, would just hamper, yeah, the heat transfer. They would just hamper each other to get the heat off and give it to the environment. So at some point, and for heavily loaded cable systems, it's not feasible. You would just damage the cable. Then you would go to the flat positioning. Yeah? Flat positioning, you would see in the slides after, it's way worse for radiated magnetic fields, but you can get a better heat transfer. So for each project section even, yeah, it's not that we say, okay, new cable line, substation A to B, this is the only system we are going to use, only trefoil or only flat. No, we would even partition the whole routing and then see for which section the best solution we can find. And it's always a dilemma, let's say, between the magnetic fields, which is really, let's say, heavily regulated, and dilemma between the magnetic fields and the heat transfer, not to warm your the underground, to be sure that the cable can live forever, almost forever. Okay, just a slide. I won't give any, let's say, detailed figures, but this is, let's say, the axis 0, just the middle of the cable route, or if you're standing in the middle of the overhead line route with a double system. Okay, if you just look in the middle, is there some kind of pinpoint here? Yeah, but I don't dare to push. Which one is it? Anyway, yeah. Okay, so the flat positioning of underground cables, it is the really pinpoint blue curve. It just, perfect, right one? Yeah, here. So that's measured with an expensive field meter. If you want to buy one, 5,000 euros for free. And then, yeah, so flat on the ground, just immediately on the axis of the middle phase, you will get the highest, let's say, effect of the magnetic field. If you would do the same, the very same, but on 1.5 meters, and that's about where humans and human heart lives, then be good that, yeah, this will sag down to about 10. It's microtesla per kiloamp. Of course, it's scaled up or down if you want with the current passing through. So even though you see that the flat comes here about, and then about a fifth or a sixth, even lower when you go to a trefoil. Yeah? So this dramatically, let's say, gives you options or would hamper you in all this design. Yeah? With the double overhead line, you stay here somewhere, and it's about, let's say, 4 here and 5 times higher, 6 times higher, the overhead line. So overhead lines, of course, what you measure is the fields coming off from the lowest phase conductors. I don't put too much figures here because it's also a really sensitive matter with respect to people living close by the 0.4 micro Tesla and child leukemia, all these kind of discussions, I leave it apart. So know that there are different regulations, also in Belgium, 3 regions and 3 different sets of limit values. So it's it can be a huge mess. Great. So what are factors to be taken in consideration? If you lay down, for example, your new cable route next to a school, for example, those are the most sensitive. Politicians really flush on this aspect. In urban environments, usually the trefoil, even if we would dedouble the number of cables, fine, but the least possible radiated or emitted magnetic fields. Rural environment can have some more, but we will see some anecdotes later on where this is perhaps really even more sensitive. The ampacity or the transport capacity is also, you need cables especially for that, but you see, having them really close together can be really harmful. Okay, the positioning of the junction pits also, if you want to apply cross-bonding and so on. So the junction pits, especially for land cables come on drums between 750,000 meters, and each 750 or 1,000 meters, you need to make a junction pit. And somebody has to crawl in and make these kind of really delicate junctions. The junction pits sometimes stick out, like here. This is a simulation for Marant Gezelle, north of Belgium there. And you see all this, the 12 cables here with the 6 junction pits also take some space. You don't want to have the cows go nearby and so on. Even more, if you need to cross canals or rivers or something else, if you need to do directional drilling, it all comes at a cost. For example, this is a tunnel, let's say, a tunnel route in Berlin, in Germany. We have kind of the same, but I didn't find a really nice picture of it. Also between Gezelle and Van Marland, so in the north of Belgium. If you need to cross a canal with these large cables, you make this kind of, it's not road tunnels, but cable tunnels, literally. So all these specifics you need to take in your in project whenever you must do. What if sometimes it's really hard to get to the limits imposed by regulations? What can you do? For example, we like to do encapsulation. Encapsulation means with sheets of copper and or aluminium in this case, and you make a sheet which would heat up and dissipate all the energy going into the magnetic or emitted or radiated magnetic fields by the cables and would just heat up here, but the fact you heat up also creates this counter currents and magnetic fields. So on the bottom, you wouldn't measure anything. We did this for a route of about 30 to 40 kilometers between the substations of Arnas and Dihange. And some people were, rural people or farmers were really sensitive about this. You would see copper sheets, welded aluminium sheets, and welding and aluminium doesn't go well together. So these people really bought magnetic field meters, 5,000, 6,000 euros, and they almost every week they would pass by the cable route to measure up if the system would work. And at some point they found a crack, and we say, and they wanted to have the cable shut down, and we say, okay, thank you, you found a crack, we would weld it again. But people, this would sound like a fun fact, but this is really how people would react to any of these high voltage installations. Right, a second method is to really, and again, encapsulate, but this is a complete magnetic shield. No heating, but just a sealed casing in steel. Imagine that you would do this for kilometers, and this particular, let's say, solution requires that there is no single gap in any welding at all. It needs to be perfect, let's say, for 60 or even 80 years long. You see how sensitive this all could come. It also comes at a right cost. Some easier things we could do. If you would ask any colleague of Elia to talk about the, the earth continuity conductor, nobody would understand it. It's the le câble de drainage, but the official English term is earth continuity conductor. So even with a cable route, you have your three phases. You would draw one or two more underground, let's say, conductors at ground potential from substation A to substation B, and any surplus magnetic field would be, let's say, would induce a voltage difference, would induce then a circulating current to even more dampen the radiated magnetic field. This is something Elia does at almost any cable route, especially in urban environments. But all the solutions I've shown already are really, let's say, already supposing that the cables are really close together and that they don't, let's say, fan out, like for example in junction pits or at cable terminals here in a substation. So yeah, for those installations, we have what we call, it's still kind of in experimental mode, these passive meshes or passive circles. I don't know how to call them in English. So even with a toroidal core around them, just to force this counter-magnetic flux, and in order to reduce to a maximum the radiated or emitted passive flux, but I wanted to use another word, to a maximum the radiated magnetic fields, right? But it's nice, huh? You bury away, perfect. You bury away the underground cable, but this reactive power from the shunt capacitance is really driving the voltage into the air. And so in your substations, you need to put these kind of devices, very noisy shunt reactors, just to draw out, to consume, let's say, it's not actually consuming, but technically seen, but to really draw the reactive power out of the system to get your system voltages down again. So if people say, oh, we don't want to see the overhead lines, put cables, then you say, you get these machines for free. That's what you're choosing for. You would find anywhere in any discussion these kind of devices. So it's an unfair discussion in the media due to these machines. Right. Impact of the sea cables, just really quick. So the sea cables, as probably you noticed already, so they need to pass the sea bottom. The sea bottom, you don't have any choice. There's marine life, there are sea currents. There are these, let's say, intricate walls in the middle of the sea when you need to decide, do I need to dig through or go around? Really messy decisions. Also, for example, Nemo cable is between Belgium and England. You pass 3 countries with, again, 3 types of regulations. And France, we passed a bit by France, and France, they were really nasty. They say, your cable there, but we don't have any benefit out of it. It just passes through. We have even more stricter regulations there. Fantastic. Shipping lanes as well. So the shipping lanes between in the Strait of Dover, for example, is the busiest in the world. And the busiest mean many ships, many anchors that can drag into your cable. So you need to really pass them perpendicularly just to minimize the risk of these anchor damages. Also, yeah, the sea bottom itself, you would say, yeah, it's just a vast sea. But relying cables and even more for maybe, yeah, the wind farms, it's all telecom, also gas pipes and so on. It's really overcrowded on the sea bottom with respect to this large subsea cables, of course. What do? Do you go over them, under them? Do you protect them? Yes, no. Very difficult. Sometimes you cut them and hopefully nobody would complain. And it happened, by the way, some forgotten telecom cables. And then the last slide, it's this really funny chart of all the shipwrecks and airplane wrecks which have been found during the survey for the Nemo cable. So on the sea bottom, you're not alone, yeah. And some of these shipwrecks painted in green here are historical shipwrecks, you know, the English people and their heritage and so on. So these are officially war graves, and you can't touch them, and you can't even look at them, or you will dragged before court because you would maybe just move 1 grain of sand. Joking, of course, but that's the kind of appreciation they give to these historical, underwater war monuments. So, and this whole package defines, let's say, the environment where we put our cables in. Most of the time, it's dealing with humans and their little sensitivities. But okay, we live in this kind of world. So, yeah, I thank you for your kind attention.
Yeah, thank you very much, Johan, for the insightful presentation and yeah, I would say all the interesting issues that you have to deal with.
Yeah.
Are there any burning questions for Johan?
Or later on. Huh?
Yeah.
Oh.
Frank?
One question on this injecting currents to counteract the field.
Yeah.
Is something that is currently being done, or is one of the solutions that you said it was being tested?
It's currently being done as a testing operation. So it's like we look into, let's say, solutions to have some up on our sleeve to put on the table if ever, let's say, issues would come. But this one is installed in Schaerbeek, and it's working pretty well. So we like to do this proof of concepts, long time proof of concepts, just in case of when we would need them. I see something flipping, but okay. I was distracted. So, so the passive loops, yeah, they're not experimental, but not deployed, let's say, at so many occasions. The other one, the earth continuity, it's almost any cable route would have them. Yeah, for sure. Oh yeah. So yeah, very good, very nice question. Maybe I skipped too much through. Yeah, and I see a typo. It's so. In the very beginning of the HVDC business, they would install just one, let's say, pole or one phase and have C electrodes to come back. Yeah? So you see there is no, let's say, real compensation of magnetic field. And ships, especially ships with magnetic compass used to be with 2 S's. And when they, let's say, go over the cables, they would see that their compass would spin. And no, this was not done. So by the marine authorities, any following cable had to be, let's say, especially for HVDC cables, but also for the AC 3-phase. So the plus pole and the minus pole need to be as close together as possible. Maybe even in the same casing or wrapped together or glued together, so as that the compensation would be almost perfect from a certain distance, 30 centimeters. So this is already very, very good for marine life, as well as for the ships and their maybe ancient magnetic compasses, but I believe that for now they would use the GPS. But anyway, so yes, this is very much, pretty much illegal and really restricted to the lowest possible. Yeah.
All right, thank you very much, Johan.
Sure.
Oh, there is another one I see, Dries. Yeah.
Yeah.
What is your opinion of India because earth electrodes near, for example, beach?
Oh yeah, you know, we won't have them. So we take the liberty to completely avoid them. So you know so a daughter company of Elia, 50 Hertz, yeah, in the east of Germany, they get the older what's called the Contec cable. So at one point, I don't remember which one, but at one point, take the Denmark side, they had the copper C electrode in the ground, yeah, and on the German side they had the huge titanium electrode in the seabed, just to, let's say, yeah, anti-corrosion wise, they need to have titanium, which is costing so much, and we would avoid them, let's say, with their experience, and we would avoid them at all costs. Yeah, that's our maybe note to keep in mind for the complete future, especially with the earth electrodes themselves. You won't get to the restrictions on magnetic field even, because the currents would disperse throughout, especially for DC. So the road towards your destiny through the cable is not a road, but that the current would take back, especially at DC. So it would fan out all over the place. You would see when you would do some magnetic field measurements that you would just see one phase of current running through, and it's just too devastating for any regulations possible.
All right, thank you. And with that, I would actually ask all the speakers maybe to come forward and have a seat, and then we can still have a bit of an extended discussion for the next 20 minutes or so, where we can then also eventually have a look if you would get some questions from the chat as well. Johan, please take a seat if you want. But maybe before going to the audience, I would like to sort of kick off the discussion maybe with the very first question. So there is obviously an increased need for, underground cables. Is it AC or DC or land or, submarine? There's an increase in the demand. But in fact, how scalable today is our supply chain? So are we going to have enough production capacities in the near future for cables, for vessels, for monitoring systems? That we can actually cover the demand to, meet the criteria for our energy transition. And maybe also as a question to Johan, are you as a TSO somewhat afraid that you're going to experience a shortage of equipment in the near or long run? So I don't know who wants to take the first answer.
Yeah, so indeed, there is a shortage. There is a shortage. In fact, there will be several shortages. The first shortage we see at the moment is the shortage of cable, which is quite increasing in high voltage. Medium voltage will come in a second step, but it already starts. But high voltage is already the case. And this is a worldwide phenomenon. This is only in Europe, but of course in Europe it's quite strong because, of course, of the transition, energical transition. And so what we have done, 2 years ago, we were feeling that it was upcoming. And so we start to discuss with the TSOs in Europe and to say, take care, because it's coming. Because we made market analysis worldwide and we found that. And of course the TSOs reacted correctly and they demanded us, how can we reserve the manufacturing slots? And so we started last year with several TSOs the possibility to reserve manufacturing slots. So we block a manufacturing slot in advance. It seems simple because then you block your capacity, you can extend your capacity because you have a long vision, so you can buy new machines and so forth, but this has limits. And the first limitation is coming from the fact that the TSOs is not, as a regulated entity, does not have the right to purchase cable in advance. So for the TSOs, Ilya are the ones, the first question was, okay, we have to knock on the door from the regulator, the CREG, and to say, okay, guys, we need money, so we have to increase the price of energy by some. Do you agree on that? So it was for Ilya a first problem to solve on their side. And then on our side, of course, to see at which speed we could increase the cable production. Then, of course, we can produce it locally. We have manufacturers in several countries, so to share the capacity we might have in Europe, elsewhere. And so any manufacturer at the moment is looking how to increase, namely with big projects like if you look to Südostlink in Germany, some cable manufacturers, they build new plants to increase the capacity. But then you face the second problem, is the delivery of the machines to make the cables. And then the manufacturer says, yes, but we are not that many manufacturers in the world. And so, because these machines are quite atypical, then they say, okay, the delivery time at the beginning is 1 year, then 2 years, then 3 years. And then you face a second problem. Even though you would like to increase your plant capacity, you have to wait 3 years before getting the machine. So you have solved again partly your problem. But then it's even going worse. We made macro analysis for example, for the mines. We went to the mines and to say, okay, let's suppose the copper consumption increase. And they say, then we have a problem because the consumption is increasing so fast that even though we would like to build a new mine, the time to build the mine and to start to excavate and to have the raw materials available is too short compared to the demand. And so you face a problem of raw materials time. So we are in a race, actually, against the time. This is what we face today to see how to deal with this huge increasing of demands, whatever the raw materials, copper, aluminium, whatever, and cables to face this increasing demand in energy. It's a real challenge. Until now, we have plants in Europe which are full till 2028, 2029. And if you go to China, it's the same song. If you go to the US, it's the same song. Many countries start to have problems. And once again, due to the fact that it's asking more cable, then more machines, then more materials, we are in a running phenomenon against the time.
So it's going to be challenging. I don't know, do you want to comment on it from,
I can vouch on
let's say,
that.
the installation perspective?
For the vessel, it's the same thing. So
Yeah.
what we are doing is we are assigning vessels to projects or even to TSOs. The Voltaire, Les Alizés, the Fleming Jenkins, they are all built for, even before they were already assigned. Fleming Jenkins is part of the TENET framework, which is exclusively used for that purpose. The same for the Voltaire and Les Alizés. So we are also looking already at 2030, 2031, 2032 for our new project. So we are also full. So there is also a need for standardization, in my opinion.
Yeah, so...
No issues in supply chain.
yeah.
just
Okay.
resources, people.
Yeah.
Yeah, I can Vache as well. By the way, it took me 3 hours to come from Brussels to Leuven. It was a huge traffic jam. But yeah, in Europe and the rest of the world, it's a huge project jam. Everybody would get there eventually. But yeah, it's looking everywhere for some kind of an opportunity to overhaul one another. But in the end, we're let's say using all the same materials coming from the same mines and the same manufacturers all over again, which has been really let's say dealt with also in the newspapers later on Elia and the Princess Elizabeth Island, which would cost maybe 5 times more just because of this huge traffic jam also with the transistor business. So yeah, it's is this epoch in the world.
But at least, I mean, it's somewhat good to hear that there is a lot of demand and there's a lot of continued demand, which sort of takes a little bit away from the investment risk, but there is still a lot of production capacity to be built. This is what I understand. One thing that many of you have actually also talked about was on the standards, and that there's actually sort of a lack or some gaps in the standard when it comes to, you know, designing and modeling and so on. But what actually does need to be changed in that respect? So what exact aspects in the standards do you think that there should be an update coming?
Well, from my point of view, there's this one very specific problem or issue that we faced. We decided to continue without the norm. Just because it's better, and it's better for our customers, and we explain it to them. The second feeling I have, especially with submarine cables, and maybe my colleagues on the left can join in, is that every project is specific, or every design is specific for the project. Especially for submarine cables, we always see a cable design report that explains the design for that specific project. So I believe it becomes very difficult for norms and standards to maintain the same pace, and especially because the diversity in projects becomes that big.
From an installation perspective, same thing. We are using actually the submarine or the offshore business is a very young business. We're only existing for actually not that long. The standard that we are using for installations, DMV 0360, is a standard that's also getting a little bit achterhaald, outdated, and needs a new update. And where we still think that there is some kind of need for standardization, because otherwise we'll have to reinvent everything every time over and over again, and it takes time, cost, and money, and maybe that is not always the way to go. The Energy Island also has its advantage because we have 96 times the same thing. So there, standardization does have its advantages.
But basically, if people know that standardization is sort of lacking, why is it then not moving any further? So what is sort of blocking for the standards to get updated? Thierry, you being involved, maybe you can give a little bit of insight?
Yeah, but first the standards are taking time to be built. I remember 10 years ago, one of our engineers found there was a fault in the 228 standard for the conductors. And he found that when you were going to a Millikan conductor, 2,500 square, copper, aluminum, the AC resistance was not correct. And so he asked, by showing to the committees, that it has to be updated. It took 12 years to update it. Because one problem with the standards, and when I was co-conveners for the overhead lines for the composite core overhead lines for the high temperature conductors, it was typical is that all the group working, or your technical group, your technical committees for many countries have to align together. And then the discussions begin. And it's taking a huge amount of time because you are speaking about two numbers after the digit and things like that, and the point, and it's extremely difficult to align everybody. And sometimes it can block a standard. One of the standards, I was project leader for the 63089 for the overhead lines as well, and we had to go back to the CEBEC committee to say we have a problem. We cannot make a standard because we cannot find a common agreement between the members. And so we made just a technical brochure. So this is the typical problems we might face by trying to improve the state. Even though we're trying to move them further and to get standardization, it's a point. The other phenomenon I found in the standards, the committees, is that some active members try to simplify what you are trying to build for just lucrative reasons. They try to sell a black box and then to say, okay, it's fine. And whilst the other members of the committee say, no, it's not fine, because we should develop and make the testing and the protocols and whatever the qualifications. But other members will try to block you. So you have lobbies in the standards that can be extremely strong to avoid that the standard is coming out too fast, because we are, as Europeans, very open, but other countries coming in Europe are trying to block Europe to develop their own standards.
Yeah, that's, I think, not very good news, considering that they're outdated, but we also have a rush of getting them updated. Johan, do you want to add something to it?
Yeah, that I completely concur with what you're saying. You completely agree, and sometimes the IEEE brochures and CIGRE brochures are considered as the de facto standard, because the IEC is just so administrative mess with the subcommittees and national committees and so on. And at the end, they're just shooting in their own foot. Yeah. Unluckily for us, all of us.
Well, I mean, you know, that much administrations, that almost sounds like Belgium. Do you have any questions, do we have any questions from the audience or maybe from the chat for the time being? There's one up there.
Depends on the technique. Let me start with distributed temperature sensing. What you get is every time you send out a laser pulse, you look at the reflection, you get reflected light. But it's processed, and there's 3 different techniques. You can process the light and look at the different types of the backscatter. One type is Raman, one type is Brillouin, and one type is Rayleigh. Temperature sensing looks at either Raman or Brillouin, but it's translated. So the interrogator translates the backscattered light, and it gives you the temperature at every meter along your cable. Assume your cable is 10 kilometers. You measure every meter, so you get 10,000 measurement points, and every measurement point, so it's an array. It's a 2D array in effect. So one dimension is position, 10 kilometers, one point at every meter, and the second is time. So you get a measurement every time you send out a laser pulse and look at the backscattered light. Now the thing is, with distributed temperature sensing, what they do is they send out laser pulses at, I don't know, 500 hertz, and they average over 10-15 minutes to get a very accurate temperature measurement. So in the end, you get a temperature measurement every 10, 15, 20 minutes. With distributed acoustic sensing, you get a measurement every time you send out a laser pulse and look at the reflection. So for temperature, you get temperature. It's Kelvin or Celsius, whatever you want, the unit you want. For strain sensing, it's strain. So it's the elongation of the fiber at that particular position. So you can imagine a power cable of, let's say, 1,000 kilometers all the way to southern France, and you pull on the cable and you elongate it with 1 millimeter, DAS will sense it. It's 1 nanostrain. So it tells you the elongation over a distance of 1,000 kilometer is 1 millimeter. Yeah. So that's what we call strain. But if we talk as we talk now, you would do it in water. You will get pressure waves that will impinge on the fiber, and the fiber is feeling a little bit of strain sense, and that's effectively acoustics that you're measuring. But it's also in a 2-dimensional array. Time, position, and then the unit is strain. Does that answer your question? No.
Okay, as we have not much time left, I actually am going to ask a question that I expected from the audience. I mean, we have talked a little bit about the scarcity, but one of the sources of, or one of the scarcities is actually also the lack of, I would say, young and fresh engineers to actually work in all these domains. And we have here quite a bit of them here in the room who are on the verge of graduating. So my question to you is actually, as an industry or as a company, what are you actually trying to do to attract young engineers at this moment? Because they are a very scarce resource. I mean, we see that the room is also not that full today. And so how are you going to get them on board from your perspective?
There are different ways. First, it's important, and namely through SIGRE Belgium, where we're members, that SIGRE Belgium is asking to industrials to be there in the committees. And this is to make a bridge, not only between, I will say, TSOs and industrials, but also with NGN, for example, our new generation coming of engineers, to make a bridge between the academic world and the industry, and to let know what we do. Unfortunately, as everybody else has mentioned, we are making something which is undersea and underground. This means not visible. So we are not visible for everybody because we are in the walls, we are on the floor, under the floor, on the seabed, and so it's difficult for you to know what we do. So of course, if you are going in the committees, if you on the IEEE or the SIGRE committees, of course, you are more than welcome to be part of the technical committees or to be interested in the fairs that are done from time to time. But it's not enough. We found that to find more engineers, we have to show us more because, unfortunately for us, we are screwed up. We have too many projects, too many cable to manufacture, too many DTS systems, too many vessels to build and to install cables. So we are in our office or on the work and on the site, and not enough to share with you. So I think in the future we have to be more visible, definitely. Elia is already making some films to be more visible what is a network, and because they are also looking for people a lot. They have so many projects that they need project managers. We, Nexans, we need as well a lot of project managers for a project, onshore, offshore. We are lacking of jointers as well. We are looking for finding jointers a lot. So we need hands to install all this, and so it's necessary to be more visible, and I think you will see, I hope, in the coming years, more and more the industrial going to the schools, showing films, what we are doing, and explaining what we are doing. It's a very interesting world, I think, that all of us here can say that it's a very passionate world. I'm there for 33 years, and I'm still having fun in what I'm doing. So please, you have plenty of companies looking for engineers.
For Jan Nul, visibility is of course less a problem because we have the vessels. When you go to Ostend, usually there is always one vessel laying there. But what maybe I can give just a personal experience. So what I encouraged at Jan de Nul, I'm only working now 6 years for Jan de Nul, but what I wanted to do, I was always able to do. So what Jan de Nul offers is actually what the person likes to do. And that is something where I think what is valuable to Jan de Nul is that people are getting, they are being heard and they can do what they want, and we have an opportunity to learn also in various directions. We go to, I'm an electrical engineer, but we have civil engineers, and if a civil engineer wants to be an electrical engineer, then they can transfer that department and they can learn it. So, and that's also where we are trying to make the job more attractive.
Mm-hmm. Simon, do you want to add something to it? How does Marlings deal with that problem?
Well, I'm looking back at a few moments where we were looking for new people. I think visibility is more of an issue for us.
Mm-hmm.
We're much less well known than Nexans, or especially Jan de Nul and Elia as well, to most people. I worked for companies that are better known, Engie Laborelec not that much, but Engie yes, and Nordex Acciona maybe in Germany. And I also had the experience that at one of those previous companies I could, there's many possibilities within a big company. Now I rather have to, I was afraid that I was going to be too much in a niche when I started with Marlings, but that is certainly not how I feel today. So I really have the feeling I can touch upon many different aspects. I'm also in Sigre. I know the discussions for getting young people involved, especially in the power community, it's an issue. We see many people fulfilling technical roles, but we see very little people taking the effort for helping the power community. Mm-hmm. Of course, the fact that there is quite a bit of lobbying involved and that you can feel it doesn't really help the image of the community. But I also learned quite a bit in the community, and I'm happy to learn from, because the power engineering world has quite a bit of gurus walking around. So you can, not particularly looking at you, Johan, but you can certainly learn from them. So it really, but yeah, I don't know, Johan, if you can add something to this.
Yes, I can. So there's no secret. Elia is hiring 600 new people in the next 4 years. 600 people, it's unimaginable. So I started in 2000, and then the high voltage grid was kind of boring. Some digital relays, that was about the most exciting then. And then after some time, the huge phase shifters came along. These huge machines of thousands of tons. And then it started with HVDC, these are the converter stations. And now Elia is building an island. This is the first in Belgium, can you imagine? So it's like, it's really the place to be if you want to be really at the source of things. And so Elia is also hiring people with generic job descriptions. You're not pinpointed to one specific task or this, even departments. So it just hire people, have them do some kind of a shifting system, and in 2 years, hopefully, people would really feel welcome and get to know themselves better to really add some value into the company. So, we are hiring definitely.
Yeah. So at least if I would summarize it, I understand visibility and flexibility as within Jan de Nul and Elia are the two main issues. And also maybe wanting to add, or it's also from my personal belief, I mean, the ones here in the room, they're already hooked on power systems, so I think we don't need to convince these guys. But I think we also have to start a bit earlier before maybe even they go to the university. Yeah, thank you all very much for being here late this hour and for the, I would say, very, very insightful presentations. And could I ask for a last round of applause for our speakers, please?